Okay, so today we're going to go over MRAM, or using the midpoint in order to approximate the area under a curve. Now, typically this is not seen with a table as much and being asked about its endpoint as much as the left endpoint or the right endpoint in regards to the AP exam, because, well, the left endpoint or the right endpoint. They're not going to give you a table and say, use this because these are the values, for Y when we're using the midpoint, blah, blah, blah. It doesn't work like that. So it is important to know this because you are supposed to know how to approximate the area under a curve with both the left endpoint, right endpoint, and even the midpoint. So in the Do Now, there is a practice problem you guys can work on. And I'm just going to pull up the homework for MRAM so that you can see what to do for a problem like this one. Okay, so there was a homework assignment very similar to this where you did LRAM, but in this case, if you do RRAM, the rectangles are of equal width. You can always factor it out. Once again, in the AP exam, if they're not of equal width, you cannot factor it out and multiply it later. Okay, you have to do each individual rectangle, multiply the width and the height of the first rectangle, the next width, and the height of the second, and so on and so forth if they are rectangles. So you can check your answers here, okay, and you can see that this is an overestimate because the rectangles are circumscribed. Same thing over here too. And I believe this was the same because the curve was symmetric where it increased and decreased. That doesn't always happen. It depends on the curve. So all of our answers may vary as far as underestimates or overestimates based on the function. So just be aware of what that is, and we'll go over that when it comes up when we get closer to those lessons. Okay, so with MRAM, what changes is really the height. How you find the width, if the width is all the same, is still the same formula that we've been using. So I'm just kind of using the same thing from the Do Now here. Same function, same A and B values for X. I just changed the value for N. So you're going to find that the width is 1/2. Okay. Now, if you were going to draw this out on your x-axis and start when x is 0, you're going to go up by 1/2, and you're going to keep going. If you were going to label what that is, okay? So you kind of keep going. That doesn't change like the width of the rectangle, but where the height is going to go through the midpoint, okay? So notice where I plotted that point. We have like another table that we use instead, and that point is coming from the middle of the width of the first rectangle. So you have to establish what that is. A lot of times students just kind of look at it. So if let's say we're starting not when x equals 0, but let's say x equals 1/2, the midpoint, the x value we need to have information about is actually 3/4. Okay, you average the two numbers and you get your answer. So whatever value that it gives you for plugging it into the function, okay, now we have that answer. And that is where we actually plot the point, as far as the curve is concerned, or the height, the height of that rectangle. So hopefully you get the idea of how to find the x values for when we're using the midpoint. Now there is a kind of trick that you can use here. You need half of the width, okay, that you first established. So if you find out what that is, okay, and you add it to your value of A, okay, in our example A was 0, so that makes it easy. But if a was 1/2, or let's say it was like 7, then you would just add it to that value, and then you find out, well, what x are you using? Okay. Now, if you are going to graph your function and graph the rectangles, you do still need your original table, whatever that is. You're still going to set it up so you can get the base and the sides to your rectangles, because they're coming from your original table, your original width, and everything like that. But as far as the height for each rectangle, that comes from a new table. So you need to create a second table if that's the case. So you can see how I started to have the first midpoint of the first rectangle and then the next one and so on. So let's see if I actually have 10, because I still need 10 rectangles. So I have 10 widths and 10 heights. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have them all. Okay, so let's actually fill in the y values. I don't know if I'm going to have room for each one, but if I run out of space, I'm just going to use what we have over here. I think that's what I'm going to do, so hold on a second. Okay, so that's our function, and 0.25, if you're doing this in a calculator, that's actually what I want to say. You're going to start the table at 0.25, and where it says change in table or delta table, you want it to go up by 1/2, because that's still the width. So it'll get from one rectangle to the next. And you know what? Let me erase this too. If I can. Hold on. I can. There we go. So let me write this out so it's not squished in there. I'm actually going to write it from the calculator. I have space vertically more so than horizontally. So 0.25 was 0.0625 exactly. Okay, and 0.75 is 0.5625. 1.25 is 1.5625. We know they're terminal decimals because these can be solved by fractions, or expressed as fractions, I should say. There we go. We're getting there. Okay, please follow along and write this into your notebooks so you have this example. I know it's quite a few numbers here. Always highlight your y value so you can see what it actually reads as, because once you get to 3.25, it starts to round it in the table, and you do not want that. If there is an exact value, use that value. And I'm writing the wrong number. This is the last value that we need, because that's our 10th rectangle's height. And so we have our table. If we're going to approximate the area using these 10 rectangles that I'm referring to, then I'm going to need some more space. Okay? So let me stop this for a second and erase. Okay, so only because our width is the same, our width was 1/2, we're going to factor that out, and we're going to add up the sum of all our y values. So I'm just going to kind of do this and write out its sum. Okay, so over here I got 83.125. If you did get a different number, let me know. So that's 41.5625 square units. Or if I did write it as a fraction, we're approximating the area to be 665 over 16 square units. All right, now some people say that MRAM is the best approximation. It depends on your function. A lot of times it is. but not all the time. So do be careful, because if functions change from increasing to decreasing or increasing again, etc., then it doesn't necessarily give you the best approximation. If your function is entirely increasing on an interval from A to B or entirely decreasing, then yes, that's true. If it's a metric, then yes, that's true. We talked about that from the homework. So those are the only instances that, yeah, it could be possible. Other functions, of course, but once it starts to vary, then it may not be your best approximation. So that's why it's still an approximation, and it's to get an idea of an area under a curve. For future lessons, we will indeed find out the exact area under a curve. Do not worry. Good luck. I'm going to post the practice. Do them. Okay, so these are your practice problems. Let me know if you need any help.